Thank you, Gianluca. Yes, as I was saying, as much as I can, but yeah, let me just start by saying that, I mean, fundamental physics is a large subject, so I had to make a selection. Selection is arbitrary and necessarily arbitrary, but so see this talk and like this lecture as an invitation to the subject. So if you want to know much more than what I will say today, so you can think to have a look at this very nice review and science case prospect studies. So I will start with this plot. I don't know if you have already seen this plot, probably yes. So what you see here is the gravitational field strength on the x and the space-time curvature on the y. And so, and here you have several probes that are either already operative, that they were operative in the past or will be operative in the future, like LISA. And so what you see is that gravitational wave observations, they lie in the top corner of this plot, top right, which means large field strength and large space-time curvature. So this means that gravitational wave observations, they probe gravity in the strong gravitational regime, okay? So by observing gravitational waves, we are looking at a strong gravity region, gravitational waves emitted from the proximity of black hole horizons or the proximity of the surface of compact objects. So you can also do some heuristic scaling argument. So if you roughly estimate the separation at the merger as the ISCO radius, so this separation will scale like the mass, and if you plug these things here, so what you find is that the curvature scales inversely with the mass of the object, which also means that if you observe supermassive black holes, so you probe much weaker curvature scales than stellar mass black holes, which is why ground-based gravitational waves is here, like it's in the top region of this plot, while LISA is a little bit lower, but both, I mean, they will probe a strong gravity region, okay? So now, of course, there are many fundamental physics questions, but let's start by dividing them into two broad categories, one pertaining to black holes and the other to neutron stars. So what about black holes? So in general relativity, so we have a pretty good understanding of black holes. So black holes are very simple in general relativity. They are described only by their mass and spin at equilibrium, and this is also called the Noether theorem. And so we know that they are stable, and they are described by, I mean, notably by a closed form space-time metric, which is called the Kerr metric. All these properties are not necessarily true if you relax the assumptions of general relativity. So black holes in general relativity are so simple that testing their simplicity can give insights into whether there are deviations from general relativity or not. So on the other hand, neutron stars are not simple, okay? So they are composed of, in the simplest model, they are composed of neutron matter, but then, so if you look at this QCD phase diagram, so neutron stars lie here, okay? So we are at high densities and low temperature, and this is a regime which is hardly probed by, for example, terrestrial experiments, okay? So if we observe gravitational waves coming from binary neutron stars, we are implicitly observing neutral matter in a otherwise inaccessible region of the QCD space diagram. So this gives very good insights into the equation of state of nuclear matter, which is presently not well understood. And also, if you are able to observe not just the in-spiral of the binary neutron stars, but also the plunge and the merger, so you start moving into this phase diagram, because then you cannot describe anymore the neutron stars as cold, but they become hot. So you start to rise in temperature, and so to explore better this QCD phase diagram. So we are interested in neutron stars because they give information about the behavior of the equation of state of nuclear matter at high densities. And so yes, so the two fundamental questions, and then we will see it better, how you can decline them in actual tests is gravity described by general relativity, and often this means is a black hole a Kerr black hole, both at equilibrium and dynamically. And the other question is, what is the composition of a neutron star? So can we understand what's really inside a neutron star? Now, let me start. Okay, look, don't be scared, but so I call this best theory because it looks like a mess. So if you go to theorists and you ask them to write a theory beyond GR, so they will come up with such things. Okay, so these are actions, and they are not easy. Well, for one thing, they were not easy to formulate, but they are not even easy to solve. Okay, so you usually study them in special regimes, like for example in the Erlin spiral regime or in the ring down regime. We will see it later, where you can expand the problem around a background solution. So we will not dwell, into these actions, and we don't care. I mean, this is just to show you that I will show you a lot of plots, but behind these plots there are complicated Lagrangians actions. Okay, so it's a hard work. On the other hand, if you look at these references, so you will see that you can already. So these are unconstrained actions, okay, that were formulated before even the first detection of gravitational waves. But they have already started to be constrained. And if you look at the archive numbers here, they are 17, 17, 17. Okay, so this should ring a bell. So these are constraints that come from 17, 8, 17. Okay, so just by the fact that gravitational waves were shown to propagate basically at the speed of light, so with a percentage difference of 10 to the minus 13. So this put a lot of constraints on these terms into these actions. So you can just open this link and see that they drastically simplify. Okay, so then you might also ask, why do we care? I mean, this is a legitimate question, no? So why are we playing this game of writing these actions? Okay, so I don't want to go into this. I will go into this at the end, because otherwise I risk to sparkle a discussion and I will not finish the talk. Okay, so for the moment, let's accept that we are interested, into testing general relativity and testing the possible presence of beyond GR effects as described, for example, by these theories. And let's go on. And if you look at this, so what you see is basically that beyond GR theories typically introduce extra degrees of freedom in the form of scalar degrees of freedom or vector degrees of freedom, sometimes even new tensor degrees of freedom beyond the gravitational field itself. So I will start by reviewing Erlin spiral tests. You already had in the first week a glimpse of that. So basically, what is the idea behind Erlin spiral tests? So the idea is, so you can describe the gravitational waveform as an amplitude and a phase, frequency-dependent amplitude and frequency-dependent phase. Gravitational wave detectors are much more sensitive to the phase than to the amplitude. So let's look at the phase primarily. And you can expand the phase as a Taylor expansion in the frequency f, which is related to the velocity of the binary as it in spirals. Okay, and so these coefficients here, these are called the post-Newtonian coefficients, and I mean, they can be computed with perturbative techniques. It's not easy to compute them, and there are still current efforts to expand this expansion beyond this order, okay? But, so in principle, you can compute these coefficients in GR, okay? So now, the idea is to let these coefficients to deviate from the GR predictions by introducing these deviation parameters, which I call agnostic, because like you are treating them as parameters per se, okay, as if they were fundamental parameters, okay? So you are not expanding further these parameters by allowing them to depend on masses, spins, intrinsic properties, and they should, okay? But for simplicity, you don't, and then we will see how do you live with this simplification. So let me call these agnostic deviation parameters, and you try to measure these deviation parameters delta phi hat and see if they are consistent with the predictions of general relativity. The predictions of general relativity is that these parameters should vanish, okay? Now, results from current LBK data. So these were taken from the testing GR paper with the third gravitational wave catalog. And so, first of all, so each of these lines represent an individual constraint on delta phi for several choices of delta phi, okay? So you pick up a choice, let's say n equal 0.5, and you put a constraint on delta phi, okay? And each line is a constraint from an individual event, okay? But of course, if you just restrict to constraints from individual event, the best that you can do is to take the better constrained event and say, okay, this is the constraint on, let's say, delta phi 1, okay? You want to do more. So you want to combine the events and obtain a constraint that is a collective constraint, a combined constraint. And why do you want to do this? And then we'll see how. But why? So the reason is that, so at least with present gravitational wave detectors, you do not expect huge signal-to-noise ratios, okay? So you do not expect that with a single gravitational wave event, you are able to put an extremely stringent constraint on any of these parameters, okay? There might be exceptions, but this is the general situation. You will not have a single, an individual detection that will allow you to put an incredible constraint on any of these parameters. So you are interested in putting all these individual constraints together. So as an anticipation, so these plots here, they show exactly the constraints on when you combine individual observations. And as you see, they vary a lot in order of magnitude. Like, for example, this constraint here on phi 6, it goes from -1 to 1, so it's almost uninformative. So it's telling you that GR is true within 100%, okay? While other other coefficients, they are more informative, like this phi 0 is telling you, is putting a constraint at the 20% level, okay? Which is still large. I mean, we know that GR is not wrong by 20%, otherwise we would have noticed before, probably also with other experiments. So fine. But how do you do that? So there are several, not many, but several strategies to combine individual constraints together and individual deviational parameters together. So when you, you start from the likelihoods, basically, okay? So you have an observation di, and you have the likelihood for the parameter delta phi as observed by the observation di. And the naive thing that you can do is to multiply the likelihoods, okay? Because, so basically the idea is that the likelihoods are proportional to the probabilities, and when you have individual and independent observations, the total probability is the product, no, of the individual probabilities. However, this way of stacking the constraint, it assumes a very strong property, namely that the deviation parameter is common across all observations. Okay, so for example, in GR, this is true. Delta phi is equal to 0. If GR is true, then it's true that delta phi is true is equal to 0 for all observations. No, but in general, so if you pick up a beyond GR theory, which is non-GR, like in general, these delta phi's will not be the same depending on the observation, because they will depend on the black hole masses, black hole spins, and so you have to allow yourself to capture this dependence within the parameter space. Nonetheless, I mean, stacking the likelihoods is not unuseful, because at least it tells you what is the best constraint that you can put under the assumption that delta phi is equal in all observations, which includes GR. Okay, so it's still the best that you can do. But I mean, like a more rigorous approach is to acknowledge that these deviation parameters they depend on the observation. And for example, what is currently done, but these tests evolve. Okay, so more intricate tests will be performed. But at least what it's done in what has been done up to now was to assume that delta phi comes from a population distribution. Okay, so we assume that each delta phi comes from a population. We don't know what is the population of delta phi, but for sure we know it's that if GR is not true, it's not a delta Dirac distribution. So what we do is to make the very simple assumption that it is a Gaussian distribution with a certain mean and a certain standard deviation. Okay, so at least to capture the dominant momenta of this distribution. Okay, and then you can write down a posterior, and you can sample this posterior with Markov chain Monte Carlo or with nested sampling, any Markov chain sampler that you like. So in this case, you are being more rigorous because you are assuming that the deviation parameters, they all follow a common distribution. And if you are interested into this, you can look at this paper which introduced this strategy. It didn't introduce population inference and hierarchical inference for population inference, but it basically introduced it for testing GR purposes, okay? And it's written in a very pedagogical way. Okay, so let's go back. So again, now we can look at each delta phi basically, and we can look at the mu and the sigma for each delta phi. Now, please observe that if GR is true, peaking at mu equals 0 is not enough, of course, because peaking at mu equals 0, but with a large spread, it means that you are not a GR, okay? So you are just sampling from a distribution that peaks at 0, but it's not always 0, okay? So you need both conditions to be satisfied in order to be consistent with GR. So what you need is that mu is centered at 0, but you also need that sigma is peaking at 0, which is the lower bound, basically, because sigma is positive definite. So if you look at these posteriors, they are very large. Some of them are very large, and some of them are more constrained. They do not show any sign of deviation from GR, and some people are happy and some people are not. You decide if you want to be happy or not. So you can then reconstruct the so-called posterior predictive distributions. So basically now you have for each delta phi the distribution of mu and sigma, and you play the game backwards, okay? So now that you have mu and sigma, so now you know what is P pop, and then you can reconstruct the corresponding predictive distribution for delta phi. So what do we expect delta phi to be? Which in general, I mean, it's not necessarily a Gaussian, okay? Like the posterior predictive is not a Gaussian, it is a sum of Gaussians, okay? It is a weighted sum of Gaussians because you have posteriors on mu and sigma, okay? You don't have a single value of mu and sigma. So anyways, so we end up with this very, I don't know, some of them discouraging, some of them encouraging, violent plots, okay? Questions on this? Okay. Now, there might be, as you have already suspected, interpretational caveats in this analysis. Why? So, because, as I said, this delta, where are they? Here. This delta phi, they are not true degrees of freedom. So they are artifacts, okay, of the parameter estimation. So you just introduce them for a matter of convenience. But if you look at like the real story from some of the modified theories that have been proposed in the literature, so each of these delta phi's has in principle a complicated dependence on both the masses and spins of the black holes, but also the coupling constants in the action, okay? And there might be several coupling constants for each theory that you propose. Like, for example, this theory is called Einstein-Adder theory. It has 4 coupling constants, okay? So then you might ask, why don't you just do the parameter estimation, for each single theory? And one good answer to this question is that we are not sure that this theory are encompassing all the possibilities, okay? So these are just few theories that people came up with. It doesn't mean that if GR is wrong, the true theory lies in this set, okay, of theories. So you want to be more general. You want to allow yourself to capture effects that are perhaps not even described by any of these theories. By the way, this is cut, okay? So if you go to this review, you will see more, okay? I just cutted the table. So in the jargon, then you can say that the delta phi are false degrees of freedom, no? They are not true degrees of freedom. And so one caveat is that false degrees of freedom, it's true that they allow you to be more general, but they can also allow you to go into unphysical directions, okay? Like to probe a space that does not correspond to any well-defined physical theory. So you have to be careful when you interpret these tests, okay? And trivially, for example, another caveat is that I said, oh, here there is a 20% constraint, but if instead of calling this delta phi, I called it delta phi squared, it would not be a 20% constraint because it would be much larger. So it also depends on how you define the variable. So you must always have in mind some true degree of freedom correspondent, of your delta phi. Then there is another caveat. So it was shown in this paper that if you devise a test for probing an effect, like for example this Brown test, this one was devised for probing modified dispersion relation. So what is a modified dispersion relation? So you imagine that instead of having that E squared is equal to chi squared, meaning that the energy squared is equal to the squared of the modulus squared of the momentum, like you would have for gravitons propagating at the speed of light. So you add modifications to this dispersion relation, okay? And then you devise a test. So basically you use a convenient agnostic deviation parameter that is parameterizing this dispersion relation. So what they did, so they injected a modified dispersion relation So this is simulated signals, okay? So this is not true observations. So they injected, and so what they recover is that the deviation parameter peaks away from zero. I mean, it's still 90% consistent with zero, but it starts to peak away, okay? And this is a simulation. But here, they are not injecting a modified dispersion relation. They are injecting another, they are changing the flux equation of the binary evolution. And still, the test that is more sensitive to detect this the change in the waveform morphology is still the modified dispersion relation test. So, just a second. So, the lesson that you learn here is that false degrees of freedom can be degenerate. So, the fact that you are applying a modified dispersion relation test, it does, and suppose that then you detect a deviation from GR, it doesn't mean that what you detected is a modified dispersion relation. Not necessarily, at least. Okay? There was a question. Great. Question? Okay. So, now, so up to now, we have looked at in spiral tests. Now, let me go into the other side of the morphology of a compact binary waveform, so which is the ring down. So what is a ring down? So basically, if you forget about gravitational waves for a moment, forget about binaries. So if you take a black hole in general relativity, you can perturb the black hole. Like, for example, you can throw a stone into the black hole, whatever, a particle that plunges, if you are more, technical, in a paper, you say, I plunge a particle into a black hole, okay? Or if you wish, you throw a stone. And what does the black hole do? The black hole reacts, okay? It is deformed a little bit, but then it was shown both with theoretical arguments, also with numerical simulations, that the black holes relaxes towards equilibrium. And how does it relax? It emits gravitational waves, okay? So if you wish, it's like ringing a bell. So you have a bell and you ring it. After a while, the bell stops ringing. Why? Because there is friction. Where is the friction of the bell? It's in the air. Okay. If you didn't have air, you wouldn't have friction. The bell would oscillate forever, but anyways, you wouldn't hear any sound because you would be in vacuum, right? So now think about this picture. So you have a bell that rings, and you have an environment which is basically the atmosphere. So now, in the case of black holes ringing, the black hole and the environment are made of the same thing, which is space-time, okay? So it's basically, so now there is no, so the medium, bless you, the medium that allows the waves to propagate is the same thing of which the black hole is made of, okay? So space-time. So we don't need two different theories. We don't need a theory for the material of the bell and the theory of how sound waves propagate in the atmosphere. Everything is described by the same theory, which is general relativity in this case. So, basically, with general relativity, what you can do? You can describe the equilibrium configuration of the black hole, which is basically the configuration towards which the black hole is asymptoting, right? So, after emitting enough gravitational waves, you will find the black hole has relaxed to an equilibrium configuration. And we know from the Noether theorem that this equilibrium configuration is a curved black hole, okay? With a slightly different mass and possibly a slightly different spin. And then you can also describe how these waves propagate towards an ideal observer asymptotically far from the black hole, like us. Okay, so the nice thing is that this condition, which is a very idealized condition that was initially studied under very theoretical considerations, is actually realized at the end of a binary black hole coalescence. So what happens, so I guess now you already know, but let me just repeat it. So what happens is that these black holes, they merge into another black hole, which, by the way, is an assumption that in GR is true by definition because of the Hawking's area theorem. So now sometimes I launch theoretical inputs just to, because that's what we are discussing, okay? Fundamental physics, okay? So sometimes we have assumptions in mind, and we might forget that they come from very fundamental physics studies. Like, for example, Hawking proving that the area of black holes must increase with time. This immediately leads to the conclusion that when two black holes merge, they must form another black hole, okay? You cannot form a naked singularity, okay? So, and then we also assume that this is true for beyond GR theories, which under the assumption that beyond GR theories are perturbatively deviating from GR, that are not massively different from GR, it's reasonable, okay? So you see, like fundamental physics is essential to interpret observations. Now, so what you end up is another black hole, which we call the remnant, and these remnant rings, okay, with these gravitational waves emitting towards the outside that are called the ring down waves. And because of the No-Hair theorem, in GR, so you ring at specific frequencies. These frequencies are called quasi-normal modes of the black hole. They are called quasi-normal because usually the normal mode is a mode that it's like a string, okay? So a string has normal modes in the sense that they would oscillate forever if they were not in contact with a friction environment. Then they become quasi-normal and they damp with time. In the case of general relativity, since the friction environment is the same thing that lets the black hole oscillate, state that they are quasi-normal, even, by definition, they can never be normal. Okay, so you have these quasi-normal modes and they are characterized by specific frequencies and specific damping times. So you see here that there is damping, okay, towards zero gravitational wave emission and equilibrium. And if general relativity is true, you might detect, 10, 12, or however many quasi-normal modes you wish, but then they must lie on a two-dimensional hypersurface, okay? They must depend only on the mass and spin of the remnant, of the final black hole. And so if you are able to test this experimentally, you are testing the hypothesis that the equilibrium configuration of the black hole is described by a Kerr metric, and also that the dynamics is described by general relativity. You are testing these two things together. And another nice thing is that you don't need 12 quasi-normal modes to do this test. It's enough to have three quantities, so just two quasi-normal modes. It's enough to have, let's say, three frequencies, one frequency, one damping time, and one other frequency. Why? Because you just have to check that you have three numbers, but they intersect all at the same value of mass and spin, okay? So this is a very idealistic, so this is a simulation, okay? This was not observed in real life yet, okay? So, but we would like to reach this point, okay, eventually. This program, this observational program, is commonly known as black hole spectroscopy because it looks like what you do with atoms, basically. So you are looking at the specific frequency of emission, and they are informative about, in the case of atoms, they are informative about the Hamiltonian. In this case, they are informative about the dynamics. How you can break this very nice prediction in two ways. Either the black hole is not Kerr, so at the level of equilibrium, the No-Hair theorem is not respected, but sometimes you have theories beyond GR in which the No-Hair theorem is still true. So in these theories, the equilibrium configuration of black holes are still described by a Kerr metric, but then you have another ingredient, so the dynamics of propagation of the waves, and that in that case would be different. So either of the two, or even both, will differ, and so quite generally, you will have that quasi-normal modes of black holes in beyond GR theories, they depart from the GR predictions. So again, so what do we know from current data? And now I will just show directly the constraints that you obtained by combining multiple observations, because constraints on individual observations are weak. So, and again, you combine with the same spirit. Yes. You technically, I wouldn't disagree with you. So what do you mean by formal? Yes. Let's say that in GR there are very strong arguments to make this assumption. No? So you have several formal theorems by Hawking, Carter, Robinson that show that under certain definition of what is a black hole, which is not necessarily the same definition that you would. So under this global definition of what is a global in the space-time. I don't know if we are speaking. Are we speaking the same language? Because from your question, I understand that you have very formal arguments in mind. Is it true? Okay. No. Okay. So there are two answers here. So one very technical answer is that, of course, there isn't a super 100% rigorous proof that Kerr black holes are the end state of the relaxation of a perturbed black hole. But there are strong arguments that are both theoretical and numerical. So the theoretical argument is that there are certain proofs by Stephen Hawking, Werner Israel, Robinson, Carter, so very mathematically oriented relativists. Penrose contributed as well. So mathematically oriented relativists in the 70s that they showed that basically there is only a unique solution that describes black holes in general relativity, and it's a two-parametric solution, and then this two-parametric solution was also found analytically by Kerr, and so they had to identify the two things, okay? So we know from theoretical arguments that there must exist a two-parametric solution, that it has a unique functional form. Then we also know that the Kerr functional form solves the Einstein's equation, so we identify the two things, but that's just part of the story, because then you perturb the black holes, and then how do they relax, and when they relax, do they really relax to a Kerr black hole? And if you look at this question from the mathematical point of view, then I sort of agree that you might say, okay, there isn't a conclusive proof of this statement, okay, which is related to the mathematical studies about the stability of black holes, okay? But if you look at this question numerically, there is a lot of numerical experiments that basically, so they are doing numerical relativity simulations in which you take a black hole and you shoot wave packets of many different shapes on the black holes, and you see how the black holes relaxes, and you always see that it relaxes towards equilibrium and towards a Kerr black hole equilibrium. So my feeling is that for the experimental gravitational physicists, this is enough, okay? But I agree that you can go as much theoretical as you wish up to a point in which this is not enough, and you start doing research on that. This I agree. I don't know if... yeah, okay. Yes. So in this case, no. So first of all, we are not very sensitive to the charge. So there have been works that have tried to put constraints on black hole charges using Kerr-Newman metrics, and these constraints are weak. But then, I mean, even more than that, you have strong theoretical arguments that, astrophysically speaking, you shouldn't form a large black hole charge. Okay, like theoretically speaking, you can have very charged black holes, or you can have magnetically charged, so electrically charged, magnetically charged black holes. From the theoretical point of view, that's perfectly fine. But astrophysical processes would prevent you to have these charges. So they would annihilate because of the environment in which the black hole forms. And probably they wouldn't perfectly annihilate, but let's say they would annihilate at the level that for all practical purposes it wouldn't be a sensitive parameter. Wow, I didn't expect this slide to trigger these questions. Okay, and so what you see here from the combined constraints, so you have combined constraints on several modes from several pipelines. So if you are interested, you can go to the testing GR paper for the details of the pipelines and the analysis. But basically what you see is that these constraints are still weak. So here we have the delta F is within 50%. In this case, I feel more confident to say 50% unambiguously, because you are mapping the deviational parameter to a physical observable, which is the frequency. Okay, so now it is still a false degree of freedom, rigorously speaking, but it has a much more physical correspondent. Okay. And same for delta F2 to 0, delta tau to 0 from this other pipeline. It is generally true that constraints on delta tau are much weaker than constraints on delta F. So people basically are more interested in delta F than delta tau. Fine, okay. These are the results from current data. We cannot do anything with this. Then there are claims, but these claims are somewhat disputed, that we have already a competitive constraints from an individual event. Not surprisingly, this event is it's 1905-21 because it is a high mass event. So a high redshifted mass event. Probably you remember from Angelo's lectures that the property that you observe is not the intrinsic mass of the binary, but it is the redshifted mass. Okay, so this has high redshifted mass. So when the mass is high, the frequency is low. If the frequency is low, you become more sensitive to the ring down, less sensitive to the in spiral, because basically you move towards the left of the sensitivity bucket of the detector. And then there have been claims that 1905-21 allows to put this constraint individually on how much the quasi-normal mode 3.3 deviates from GR, which is competitive. I mean, if it is true, it is a much better constraint than all these individual events combined together, because this goes to minus 0.05 to 0.05, and this goes from minus 0.1 to minus to plus 0.1, right? So it is 10% level. Although, I mean, not everybody agrees that this is confident. Okay, so let me call it tentative, just so I do not. So this is a fair account, let's say, okay, of the ongoing discussion. You can also see this paper for a reanalysis with alternative consideration, like, for example, what we can extract from this event is not a constraint on the ring down deviation, or how much the GR ring down deviates from GR, how much the black hole ring down deviates from GR, but basically that there is indication for precession from the ring down only. Okay, so you can play with this data and reach different conclusions, but it's so I think it's interesting to show that we are going towards basically an era in which black hole spectroscopy is starting to become feasible with individual events. And recently, I mean, a few days ago, there has been this announcement of a new event, which will probably lead to similar analysis. Okay, I'm not, by the way, I'm not part of the LIGO-Virgo-Kaggle collaboration, so when I say will probably, I'm not trying to hide things, I just don't know, okay? So then what about the future? So future is bright for several testing GR science cases and also for ring down. So in this paper, which is, no, sorry, it's not this. Okay, this is just specific for this plot. But if you go to this paper here, Science of the Einstein Telescope, you find similar numbers for not just for ring down, but for other tests of GR that have been proposed. And so the numbers are extraordinary. Like we expect to detect per year above 10,000, probably even 20,000 of ring down. Okay, like individual event ring downs with an SNR that is above the threshold of detection. But when I say SNR, I mean ring down SNR only. Okay, this is what we expect. This was done with the network of either a triangular or 2L-shaped Einstein telescope plus Cosmic Explorer. And out of these, many, like hundreds, will have SNR larger than 50. And out of these, more than 10 will have SNR larger than 100. Just to give you a scale of what it means, the SNR, this event has SNR 12. Okay? So if people are discussing whether this event is interesting or not, and it has an SNR 12, so in the future, we might be in the condition of discussing about 100 events with SNR 50, okay? So more like 4 times louder than this. And then these are just individual events. Then you have to imagine that you will combine them together using hierarchical inference and probably even more sophisticated hierarchical inference techniques than the ones that are used nowadays. So the prospects look very bright. Like this, for example, is a prospect of this deviational parameter delta F, which is the same that was tested in this real event analysis here. And you see that at 10% level of constraint, which is the same that you have here, you will have now 1,000 events approximately per year, okay? And then you will have few, like 2, 3, that will have percent level, okay, of precision. Okay, you may say, okay, 1, 2, 3 is not it's not a big number, I agree, per year, but then you have the possibility of hierarchically combining these 1,000 of events, for example. Okay. By the way, these predictions, just to connect me with other speakers, these predictions were done assuming a population of binary black holes as predicted by Michele Amapelli's code. Okay, so it is one of the most realistic predictions that can be obtained by now with an update BBH POPSINT code. So now, I mean, I said at the beginning that you don't want to do, wait, is it late? Yes. So you don't want to do theory-specific tests only because you want to be generic, but at the same time, for those theories for which you can do theory-specific tests, you might say, okay, let's do them, okay? Which is what people did. And unfortunately, you cannot do theory-specific tests for many theories right now because it's difficult. First of all, it's difficult to do numerical simulations of binary black holes in theories that are non-GR. Okay, this is an extremely challenging research topic. Okay, and there are only few waveforms. I mean, not few theories, few waveforms that have been produced using numerical relativity codes that evolve black holes beyond GR. So it's not feasible to do like a template search, a parameter estimation in the same way that you would do for GR, like, you know, using all the numerical relativity simulations that you have, surrogating their information and setting up a parameter estimation. So you have to be very clever, play very clever. So like in these two plots, they show constraints on this length scale that appears into this general coupling between the metric tensor and the scalar field in a theory. It's a specific theory beyond GR. I don't even know if I like it or not, but I mean, at least it is something that people could compute. Okay, and they have put very stringent bounds from this event, which is 230521, and these bounds come from the fact that this is a black hole neutron star event, and in these theories, neutron stars do not develop any scalar charge. So think about this phi as a field, like the electric field. If you are the electric field, you can give things an electric charge, and then similarly you will develop a scalar charge. Okay, in such theories, but black holes do. So they used this fact. So it's a very fine-tuned model, okay? Like if you didn't have that black holes develop scalar charge, you wouldn't put such stringent constraints. Indeed, they have not put such stringent constraints in general, but only with these Lagrangians, okay? And then this comes from the ring down. So now this is a different coupling, and people, after years of attempts, have been able to produce spectra of ring down beyond GR for such couplings, and then they have placed the best constraints that they could place, which are not very nice, but they are the best that they could place from ring down right now, okay? And I mean, all these things required a lot of work. So, I mean, this is just to tell you that just looking at the plot, you might think that the results are modest, but the efforts were not, and they will continue. Now, let me go to the second problem, which is the problem of, so okay, let's forget, probably some of you think that I was talking about sci-fi, so let's go back to more grounded things. And so this is a very interesting fundamental physics problem. So what's inside neutron stars? So people know what's inside neutron stars up to a certain, so you can think about a neutron star as a layered object, okay? And you know quite well, not perfectly, but you have a very good idea of what's in the outer layers. So you have neutrons, electrons, muons, okay? But you don't really know what's in the innermost layers. So there are all the possible hypotheses. You might still have neutrons, or you might have hyperons, like strange quarks. So you might have free quarks, like a plasma, okay? And all these things, why do we care? So like what is the macroscopic effects of this uncertainty? You can see it here. So take a bunch of equations of state. By equation of state, I mean you make hypotheses about the composition, and you reach, so you end up with a correlation between the density and the pressure of the neutron star. So for each density, you have a corresponding pressure. So like, for example, of course, here the density is much larger than here. And then you have a curve called the equation of state that tells you at this density what is the pressure, at this density what is the pressure, okay? And then you can use it to solve Tolman, Volkov, Oppenheimer equations. And then get a mass radius profile. So then you will end up with such curves that tell you at this mass, for example, 1.5 solar masses, what is the radius of the neutron star. And so you see, so these are all equations of state that are proposed based on nuclear physics argument. And so you see that there is a large uncertainty on what should be the radius of the neutron star. Is it 10? Like a typical neutron star, you can think about the neutron star between 1.3 and 1.6 solar masses, and then you don't know if the radius is 10 kilometers or 13 or 14 or 15 kilometers. Okay, so why gravitational waves have what they have to do with this? there is another property which is related to the equation of state of neutron stars, which is the so-called tidal deformability. So if you change the equation of state, if you go from a soft towards a stiff equation of state, you go from a small towards a large radius, but you also go from a small towards a large tidal deformability. What is tidal deformability? So take these two snapshots from a numerical simulation. These are two neutron stars that are orbiting each other. As these neutron stars approach each other, their matter starts to be deformed, okay? It starts to, to be deformed by what? By the gravitational attraction of the companion, okay? And the parameter that drives the main effect of the deformation is called the tidal deformability. And different equation of states have different tidal deformabilities. So you might think that there is less variability, but please look that this is in log scale, okay? So actually you have quite a lot of variability in the tidal deformability. So since 17817 was a golden pot, okay, and a very lucky event. People hoped that it would repeat, and it didn't. So we have to live with that event alone. 17817 was a relatively bright binary neutron star, and it allowed to measure the effective tidal deformability, which is basically the weighted sum. It's akin to a weighted sum of the individual tidal deformabilities of the two neutron stars in the binary. And then from the measurement, you can see which equations of state out of these, for example, but also if you have others, are more compatible with the measurement. So the measurement is, it has a large uncertainty, but not as large as to encompass all the equations of state. Like even in this table, for example, you can see that these are log 10 bias factors of the equations of state that you find in this plot relative to the preferred one, which is this WFF1 equation of state, whatever it is. And so you see that there are even equations of state that are excluded with a log 10 bias factor larger than 2, which means that they are suppressed by more than 1 over 100, okay? And this is with 17817 alone. Then you can do more, like you can do multi-messenger astrophysics, so you can combine observations from the afterglow, so basically the electromagnetic counterpart of this event, but also from the observations of pulsars, okay, that have nothing to do with gravitational waves. So with pulsars, you would exploit the relation between the mass and the radius, thanks to the nanograv pulsar observations. And then with tidal deformabilities, with gravitational waves, you would exploit the correlation between mass and tidal deformability. And you can place people like, for historical reasons, to translate the constraints into what is the radius of a 1.4 solar mass neutron star. This is nothing special, okay? There is nothing special about 1.4. It's just it's a convenient number to report. And so you see that these are all different analyses of the same data, okay? So you cannot multiply these posteriors together. They are just different results with different assumptions, different parametrizations, whatever, but they all cluster between 11 and 12, so in this region, okay? So we have already started to place constraints on what can be inside a neutron stars, aided also by gravitational wave observations. And finally, so now let me really go sci-fi. So as I said before, we have Hawking theorem. We know that black holes exist. We know blah, blah, blah. Okay, now what if we don't know? So, so basically, there is this exotic compact object proposal, okay, which is itself an exotic proposal, which is, what if black holes are not black holes? What do I mean? So from the outside, all the properties of black holes can be reproduced by assuming that this is a very, very, very compact object, okay? Like much more than a neutron star. It shouldn't necessarily be a black hole to reproduce all the current observations, any observations. Even the observations at the center of our galaxy. So what we know actually, so we identify all these observations as black holes because it's so compact that we don't have a theory to explain such compactness unless it is a black hole, okay? So there is this theoretical framework that tries to put this hypothesis to the test. What if we don't yet know a mechanism that allows us, sorry, not us, but it allows matter to be very compact but not collapse into a black hole, but compact enough that basically all our observations are very similar to what we would have if it was a black hole. So like, for example, this is okay, so you can probe this by perturbing again. So you play this theoretical game. Let's not yet talk about observations, okay? You play again the theoretical game of, okay, if it is not a black hole, I should be able to probe this, and in the same way that you probe stuff, like perturbing them and observing the dynamics. And then, in general, even in GR, there is the perturbation dynamics that is a Schrödinger-like equation with a potential, and this is the potential for a black hole, okay? In variables R star that goes to minus infinity at the black hole horizon. Now, if you don't have a black hole horizon, this is just a compact object, okay, but not a black hole, so you will have, like, for example, this is a wormhole, and the potential will be done like this. Or it is not a wormhole, it is actually a hard compact object, then the potential will be done like this. In both cases, like far from where you expect the horizon, you have a behavior which is very similar to that. The potential behaves as if it was a black hole, basically, okay? But as you start to go inside, like towards where you expect an horizon to be, so you have a different potential structure that creates a region where the modes are trapped, okay? And after a while, these modes that are trapped will leak. Part of them, they will leak towards infinity, and they will generate so-called echos, okay? So they are called echos. So people are very very good in selling names. So you have this paradigm of echos from echoes, okay? Or echos from echos, I don't know. But anyways, so what happens is that now if you perturb something that is not a black hole, you will have a ring down, like if it was a black hole, and after a while, which is actually a very long time, you will have wave packets, okay? And this is just because the inner boundary condition when you solve this equation is different. And so you will have these wave packets, and these wave packets will repeat and will be dampened, okay, at each repetition. Yes? Yes, but okay, I will answer in 2 slides, okay? So just wait a couple of slides. Not because the answer is in the slide, but just because I want to finish this, and then I will go back to the question, because it's a very interesting answer, and it's a very interesting question, and the answer is very interesting as well. So these echos have been searched in the data. As you might expect, they have not been found. And this was expected because, I mean, if we have already some difficulty in observing individual ring downs, individual ring down is this, how can I actually observe these echos? I mean, that you have to imagine that these are noiseless predictions, and you have to put the detector noise on top of this, and then this is in units of the total mass of the system. So like, for example, when you observe a black hole ring down, the typical duration of a black hole ring down is, what can it be like? I mean, you want to be non-conservative, it will be 10 milliseconds, for example, okay? Sorry, 100 milliseconds, 0.1 second, okay? So now you have to wait approximately another 0.1 second to get to the first echo wave packet that is very, very dampened, okay? So if we have, if we struggle to observe this, so we do not have realistic hopes of observing this right now, which doesn't mean never, okay? But right now, it is a fair, bet that you would not observe, but why not search for it? I mean, it's basically, it's for free. So just look for it and see if you find it. But by the way, they have looked for them, for ecos, and they didn't find ecos. So if you are not familiar with this is a PP plot. And so what they do, they construct a background statistics and they count how many times your statistic, which is the bias factor, it has a p-value smaller than what you expect from the background noise, basically. And if the cumulative distribution of the p-value is consistent with the diagonal line, then you say, okay, then the null hypothesis is not broken, so there is no echo in the data. Okay, then you would say, no, but this is not consistent with the diagonal line, sure, but then there is Bernoulli uncertainty, whatever, okay? So it's a very interesting piece of data analysis, how to build a PP plot, especially, it's very pedagogical, but we don't have time now. But so basically this plot just shows that no sign of echo was found. Then your question is, why would it be different? So this is the last slide. And it implicitly contains the answer, and then I will make it explicit. So let's ask the question, why do we test gravity with gravitational waves? In general, why do it's a more general question. Why do we test gravity? No? So there are some things that are at odds when we observe gravitational phenomena, okay? Like, for example, the dark sector of the universe, dark matter and dark energy. And I'm not just saying that you should think that there is modified Newtonian dynamics, whatever. Okay, I'm just saying that gravitational phenomena, they do not, they alone, they cannot describe observations of the universe. And then we have to introduce dark matter and dark energy. In that case, we say, no, then gravitational phenomena describe the universe. It's just that the matter is not, okay, fine. Then, and this is an observational fact, okay? Matter plus gravitation is not enough. Then you have theoretical problems, like, for example, inside black holes, you have the development of singularities. And singularities are regions of the space-time where the theory, it loses predictability. So basically, it signals a breakdown of the theory. And people don't like that, okay? They say, okay, if GR is the correct theory, it shouldn't predict absurd things such as singularities. Therefore, GR is not the correct theory. It should break down at some point, at some energy scale. And we don't know what is the energy scale, but you might say, no, but look, but this energy scale should be very high. Okay, so we shouldn't be interested into this when we look at gravitational waves, because these breakdowns will happen at such a high energy scale, which is not even comparable with the gravitational energies around the black hole horizon. This might be true. It might be the reason why there is no sign of deviations from GR. Okay, and then there is this other theoretical argument, which is, so Hawking discovered that black holes radiate. Of course, astrophysical black holes do not radiate because they are in a bath of cosmic microwave background. There is environment, so they are constantly fed by stuff. But if you place a black hole, you cannot. But if you could place a black hole in complete isolation, it would undergo this process of Hawking radiation, and it would evaporate. And then Hawking found that this violates, or it is in conflict with the rules of quantum mechanics, which people are also not happy about, because they believe that all fundamental forces should be described by quantum field theory, and so by quantum mechanics. And so this is not nice for, I think, most 99% of fundamental physicists. Okay, so this is just to say that these are questions that do not yet have a definitive answer. Even when you say dark energy or dark matter, you don't really know what is dark energy. It might be a viable framework, but you don't know exactly what is dark energy and dark matter, not as much as you know that the electron is a Dirac quantum field or the quarks are, SU3 blah, 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 quantum fields. I mean, we don't have this profound knowledge of these phenomena, so we have to be open-minded. So we have to be open-minded to look for deviations from GR. And then there have been, in particular, okay, now I'm answering you, okay? So when you look at these two things, okay, and in particular the third, so there have been theoretical arguments that they have argued that if you want to reconcile quantum mechanics and general relativity, you have to abandon the idea that there is an horizon, okay? Like, that's not a theorem, okay? It's an argument, okay? It's much less robust than believing that the black hole will relax to care, okay? But these arguments suggest that one way to reconcile quantum mechanics and general relativity is to drop the idea that there exists an event horizon. One such argument actually came out on Physical Review Letters this week. So the people are keeping producing this kind of arguments. So there was this paper by theoretical physicist Rafael Busso, who showed that either you drop general covariance or you drop the existence of the horizon, and he doesn't want to drop general covariance for his own reasons. And then he says, no, then let's abandon this idea that there is an horizon. These ideas, for example, are called firewalls, okay? So you have a firewall, you don't have an horizon. This firewall proposal originally came out in 2014, okay? But so you have these sort of arguments that show that the fact that you have a conflict with between general relativity and quantum mechanics doesn't mean that it doesn't have observable consequences, because it should be at Planck length, Planck time, Planck scale, whatever, okay? I don't know if I answered the question, which you might not like, but so it's a very extravagant, argument line, but ultimately it's a valid argument line. Okay, so there is this ideal me that believes that this is a real motivation, to test gravity with gravitational waves, because we want to study fundamental physics, and so we want fundamental answers. But then there is another me that is not ideal, okay? And so when I feel less ideal, I still find answers to this question, because, first of all, there is nothing to lose, and you do not build Einstein telescope or LIGO or LISA to test. So you do not ask 2 billion just to test gravity and not finding anything, okay? There are so many science cases, and testing gravity sometimes becomes a side science case, and it doesn't require much effort, because these data are anyways collected for astrophysical purposes. So you have the data for free, the infrastructure for free. You just have to apply your theory to the data. It's almost a zero-cost operation. So why shouldn't you do it? I mean, you are looking for something, then just look, and if you don't find anything, you don't find anything. And then it's objectively the best way to test the limits of GR in the cosmos, because, again, you are looking at a strong gravity region. And then let me just finish to say that, so I hope that in the future there will be more theory-specific, theory-based tests, but I have the feeling that for the time being, so at least even for ET, we have to go on with agnostic tests. So we have to find a good balance between solving actual theories and going on with this false degrees of freedom strategy, and probably introducing more data analysis techniques to relate these false degrees of freedom to the true degrees of freedom. And that's it. Thank you.